record. All right, and we're back. Back to physics. Let me see. We're missing a few people, but I'm sure they have very good reason for sleeping in and not attending physics class, which is fine. Is the sound a little bit better today? I turned up the noise reduction stuff. Better?
Okay. I'm not sure. I don't remember the audio from.
Okay. I found out one other thing that's useful on Zoom is if you're muted yourself, you can just hold down the space bar to speak so that you don't have to fumble for the button to unmute yourself. So that's kind of useful. All right.
I use space to unmute myself.
That's what I just said. Yeah, you can use the space bar to unmute yourself if you're muted. So last time we were started discussing magnets. So the basics of magnets are all pretty, things we've learned a long time ago, probably, right? If I've got two magnets and I've got opposite poles, then these two guys are going to attract. And if I have opposite poles, then they're going to repel. And that's nothing new. We've learned that you can't have a magnet without both a north and a south pole. That if you break apart a magnet trying to isolate the north pole, you get a smaller magnet with a north and a south pole on it. So it turns out we can't get poles by themselves. And we're going to discuss how these guys interact using the same description that we did when we were talking about electric fields. And so before we talked about electric fields, and we said that every place in space has got an electric field that's got some direction and some magnitude, and we can say that about every place in the world. We can say that every single point, there's an arrow you can point to, which is the direction of the magnetic field, and there's a magnitude of the arrow, how strong the electric field is right there. So similarly, we can write the same thing for magnetic fields, and instead of using the symbol E, we're going to use the symbol B. And I have no idea why we're using B. It's just a thing. So that means if I'm near a magnet, that means I'm going to feel a magnetic field near that magnet. And crudely speaking, what this is describing is which way a compass will point if I put a magnet near it, if I put a compass near it. It describes the direction of the magnetic field, which then the compass aligns itself along because it's just another magnet. And if we continue these lines, we can do the same thing that we did with electric field lines. We can draw them as continuous lines that go from one place to another. So for instance, so you remember perhaps how to draw the electric field lines for this situation, or the magnetic field lines for this situation. So just take a moment and remember how all of the lines work for this guy. If you have a piece of paper, you can hold it up to the camera to show me you've got it. Matthew's being shy. He doesn't just have no pants, like the rest of us. Is that breakfast popcorn? Oh, okay. All right, just quickly flash up in your camera what you've got there. Let's see if we can see some of these. Oh, about half of them. Yeah. Yeah, I guess you're, yeah, there's too much light in your room. I bet no one's ever said that before. Yeah, now these are all good, but they're all missing one thing, right? So you've got the lines correctly coming from the North Pole and going to the South Pole. So the lines are coming like this. But remember that also we can infer that the lines go through the magnet on the inside as well. So there's lines that run like this as well as outside. So outside the magnet, the field runs from the North Pole to the South Pole, and inside the magnet, the field runs from the South Pole to the North Pole. We know that because if we cut open the magnet at any place, this is going to be the field we see if we put a compass in it. Just as if we take a magnet and break it apart, we'll see that field inside the magnet. So that's an important thing. So now how would you do something like a field for like a horseshoe magnet? So what would the field for this guy look like? Do a quick sketch and show me. Just a couple of lines is all you need. Yeah, it's gonna have to look something like
the
that.
shape of the magnet?
Yeah. Well, you know that the lines are going to come from the North Pole to the South Pole, right? You're going to have a couple lines that look like that. But then these lines have to go somewhere. And so these guys are going to have to trace back through the magnet somehow like that. It's a little weird, right? We don't tend to think about these things. And so what's happening is that this metal, this magnetic material, is shaping where the magnetic field goes, which isn't that weird because we know like conductors shape electric fields as well. So it's a little bit more, it's a little bit of a different situation than we had before. The other two things that we learned is that if you have, charges don't create magnetic fields. They don't interact with magnetic fields. If I have a single charge, it doesn't feel a magnetic field and it won't make a magnetic field. But I have a current can make a B field. And if I have a magnetic field, and if I have a magnetic field, it makes a force on a current carrying wire. And so this first one we found because we could take a wire and we could see that the compass deflected when we put it near the wire. And the second one we saw is if you have a magnet and you run a wire near it and you run current through the wire will move and it'll slip forward or back. And I'm not going to repeat that demo because it's really hard to see. And you guys should have all the materials in your lab packets now. And I think Robertson's sending out the lab packet instructions today. So later today, you'll get the instructions for the stuff you can walk through. And then you can walk through it at your own pace. We'll be available online on Tuesday to sort of help you with things and get you up and running with some things if they're confusing. But basically, it's self-explanatory. You should be able to do it yourself without a lot of hand-holding. So this is the current situation. We know there are magnetic fields. We know that currents can create magnetic fields and that currents can feel magnetic fields. And in particular, we had a rule for how you could feel the creation of the magnetic field, right? So if I have an object carrying a current, and the current started traveling in the direction of the Sharpie, you take your hand, you wrap it around the wire, and that tells you which direction around the wire the magnetic field is going. So if you look at his fingers, they're wrapping out in front of the wire. On our side of the wire, they're going to the right. And so you know that in front of the wire, it'll look like this. So if I have a wire that's carrying current like this, that means on this sheet of paper, if we're going to draw the magnetic field lines, at any given place, they'll be headed in this direction. So right here, the magnetic field is that way. And right here, the magnetic field is that way, tangent to that circle. Or if we complete them, they draw these circular magnetic field lines. Right? Let's see, I think we've had this before, but this is a quick review. Right. So the E's have it, which is the correct answer, right? If I put my thumb along this guy, my fingers underneath will wrap around and be pointing out of the page. And so this thing is an arrow that points up towards the screen, out of the screen for you, than the E direction. Stephen, are you with us on this? Or just
I was confused because it's a 2D piece of paper, so I thought it was just over, off the.
yeah, right. So you imagine the sheet of paper is cutting through the wire, so half of the wire is sticking out, right? So or the wire is sitting on the piece of paper, so right here next to the wire. So that's how we're drawing these pictures. Is always we're taking a cross-sectional plane through space and asking what's happening at that point. Yeah. Okay. Good. I want to make certain we know where confusion is happening. So now a really interesting thing about this is that now when we're talking about magnetic fields, every time we draw a magnetic field, it's creating loops. And right now I'm doing things slightly out of order from the textbook because I think it's more interesting. So right now I want to back up a little bit and go back to some ideas that we talked about with electricity and see how they work with magnetism. So you remember that when we talked about electricity, we were talking about Gauss's law. And so I want to go back to that and think about that again. So last time when we were talking about electric field, we introduced this idea of flux, an electric flux. And what we said this is equal to a field times the area the field is going through. So if I had a surface and I had a field punching through it, an electric field, I would take how strong the electric field is there multiplied by the area of the surface it's punching through, and I'd call that the flux through that surface. But we also wanted to make certain, we also had this notion that if I had this sheet and the electric field was running at a different angle, we would take that into account. So we used the dot product between the electric field and the surface, where we define the surface vector to be in normal to the plane. So if I have, something like this, okay, gotta look at the camera, right? So if I have, so this is my plane, that might be my normal, and so the electric field is going this way, I have a positive flux, and if the electric field is going this way, I have a negative flux. So, where's my thing? Okay, so, and then if we had many surfaces, right, if we had to add it up over different surfaces, we would write something like the integral of the flux dotted with all of the small components, right? And what we found was, and why this was interesting, is that this gave us Gauss's law. So Gauss's law was the Q inside a surface over epsilon naught is equal to the flux through that closed surface. So this thing, this flux, represents number of field lines. That is the number of lines that punch through a surface. And that's how we were doing Gauss's law, because we knew that if you had a positive charge inside a place, the number of field lines that punched out of that surface would tell you something about how big that charge was, or what the net charge was inside the box. So we had a whole thing about that. So obviously we can write the same rule, or we can write the same symbol for electric field, right? So I can write that I've got an electric flux, which is going to be the B field times an area. So now if I have a B field, maybe I'll use a different thing here. So if the B field can be red, and so if I have a B field punching through a surface, it tells me it now creates a magnetic flux. So this is magnetic flux. So this is the number of B field lines that punch through the surface. So now, let's ask a few questions about this to try and get our head around why this might be an interesting concept to talk about. Okay. So I'm seeing zeros. Why are you guys answering 0?
Because electric things, if it doesn't leave, like with the lines, if it comes back, that means the flux is still 0.
Well, let's just look. So this is a simple, I think you guys might be getting ahead of me a little bit after reading the textbook. So let's look at this. So if I have a North Pole here and a South Pole here, what do these lines look like? They're going to look like this, right? So if I put a surface right here, I'm going to have more lines going up or more lines going down, or an equal number of lines.
2 lines going out.
Right. So here I would expect a net flux, a positive flux, right? A net flux going up through this surface, not down. Is everybody with me here? Getting what I'm going for? Okay. So now let's say I did something a little different. Now let's say I put the surface so it chops through the magnet, but it's not very fat. It's just a little bit thicker than the magnet is. So this is like doing something like, let's see. Take a piece of paper and put it halfway through the magnet. All right, so it's something like this. Or I can't get my magnet apart. So something like that. Okay, so let's draw this again. So we have north and south. We have our field lines doing this. All right, is that picture right? Do I have the whole picture here?
Shouldn't there also be lines through the whole magnet?
Right, that's exactly right. So I've got these lines. So now for that surface, now do I have more lines going up or more lines going down?
More going up.
More going up. So the right answer here, was upwards, right? And then the right answer here was also upwards. I'm putting this on so if somebody goes and skims back through the lecture, the video lecture, they can see which things they were. They haven't listened to my dulcet tones. Okay. Everybody with me here? All right. So here's one. Now with those two in mind, how is this going to look? I put a very big surface through the middle of the magnet. So why are you guys? So I'm seeing a lot of A's. Why 0?
Because the line's going to go down through the square and then it's going to come back up again.
Right. So you're
Assuming
saying
it has the inside and the outside lines in it. Yeah.
yeah. So this line punches down and this line punches up, right? So that's pretty good. But this plane doesn't go out to infinity, right? So there are a couple of lines like this that the plane doesn't intersect. So if I'm going to take those into account, which answer should I choose here? Right. So that answer would be that one. Whoop, I pointed the right one here. Right, it's going to be small and upwards because all of the field lines go up to the middle of the magnet, and most of them make it back down through this thing. But there's a few of them that'll leak around the edges here, right? Okay, very good. Right, you guys are getting it. You guys aren't choosing the answer I want, but you're choosing one that's a very good answer. All right, so now Everyone's gonna be happy about this. So now I've got a cube sitting around the top side of the magnet. Now, what's the net flux through this thing? Right, now it's 0. Right? Because every line that punches out here has to come and punch back in again. So every line that leaves this North Pole comes back in on the bottom, right? Now, in fact, this is going to be true no matter where I put that cube, right? If I put that cube right here, it's still true that I have the same number of lines punching in as punching out. If I put that cube, you know, over here, okay, maybe a single line moves through it like this, right? But now, if you look at this, you can see why this is that this is just a natural function of how a magnetic field works. If magnetic fields always come in loops, like for instance, if I have a wire through here that's making a magnetic field, or if I've got a situation like this, if it always comes in loops, then you can never draw a surface where I have a different number of lines coming in and going out. That means that I always have, for magnetic fields, it should always be true that the flux through a closed surface has to be equal to 0, no matter what I'm doing, no matter if I have a magnet nearby, if I don't have a magnet nearby, anything like that. Now that's really interesting, because what that's telling us is that for electricity, we had Gauss's law. So here's the equation for flux for Gauss's law. So that's flux. And then, so that's for electricity. And then for magnetism, we have that the flux is always 0. The flux through a closed surface is always 0. So this is one of these very interesting situations. These are very similar looking formulas, right? But in this case, it tells you about how much charge is in there. In this case, it tells you how much none. Now, another way of stating this is that there's no such thing as a North Pole that sits by itself. If we could have a North Pole sitting by itself, it would create magnetic field lines that look like this. And then we could draw a Gaussian surface around it, and we would see here that B would be greater than 0. If you could ever have a North Pole sitting by itself. But we can't. We always have to have a South Pole, so these lines will always connect and go back through. So you always have the same number of lines come in and come out, because you can only have loops. So there's 3 statements that we can say are the same thing, is that B fields loop, or that we can say equals 0 for closed surfaces. Or we can say there's no magnetic monopoles. And these 3 statements are all the same thing. That is to say, you can't have a North Pole by itself. So you always make loops, and if you always make loops, then the flux to your closed surface is always 0. Now, I kind of like introducing this at this point because I don't have to do any real math, right? I'm describing it mathematically, but the ideas are not mathematical. The ideas are geometric. They're things you can see. So, you know, and it's easy to look at this and just have your eyes crossed because it looks like such a complicated formula, but it's not. The idea here is really very simple, that loops mean that you can never find an end of a loop, and you can never find the end of the string. And if you can't find the end of the string, then the string leaves, it has to enter again. So that's the idea behind, so we can call this, and we don't actually have a formal name for it, we just call this Gauss's law for magnetism. So there's Gauss's law, and there's the magnetic Gauss's law, or something like that, usually called something like that. It's a similar idea that works like this. Now, if we ever did find a particle that has a north pole by itself, then we would have to modify this equation, and we're ready to do that. The minute we find one, we're going to rewrite all of physics. That would be awesome. One thing that's maybe not obvious is that physicists really, really want to break the laws of physics, because then that way we can discover things and make money, and we get grant money, and that's good to discover things. We would really like all of this to change. But that, as far as we know, with some extremely good testing, this remains true. Okay. So let's go back to one of the other things. So we've discussed the field due to a wire, and the field due to a magnet. Now I want to come back to the force on a magnet, the force on a wire due to a magnet.
Yeah, can I something?
Yeah, absolutely.
So I just read a news article recently where, like, with graphene, they found some interesting magnetism states with it.
Mm-hmm. I don't know anything about it. Graphene's a weirdo material, though, so I wouldn't be surprised that it has some weird magnetic qualities. It has some weird electrical qualities, too, so it's neat. Okay, so this was so here's the situation, basically the thing I was showing you earlier today. This is a little, just rewritten a little bit. So here, imagine I have a U-shaped magnet, right? And then I have a wire that's running from above the page into the page. This is what this is showing. So if I'm running it this way, there's a magnetic field from right to left. And if the wire is running into the page like that, then the wire feels a force down. It turns out that if we run the current the opposite way, so all we're doing is so here, between here and here, all we're doing is switching the battery around, then the force will actually be acting the opposite direction. So if the current is coming from behind the page to in front of the page, then the force will be up. Now this turns out to be a fundamental rule of physics. And this is not just, and it comes partly from our convention of what we call positive and what we call negative and what we call north and what we call south. But given those conventions, this is a fundamental rule of physics. Now, the thing you'll notice here is that there's three different directions. There's the direction of, let me see, there's the direction, so let's take this picture here. There's the direction of the magnetic field, which is to the right. There's the direction of the current, which is into the page. And there's the direction of the force, which is down. And you see that these three things are at right angles, which makes it extremely awkward for doing, like, in a 2D representation like what we've got here. So you need a rule for saying which way it'll go. Now, if I flip either one of the red or the blue ones, then, or either one of the blue and the black ones, I should say, then the red one will flip. That all three of these are always at right angles to each other. That if you have, that the resulting force, the red one, will always be at right angles to the current and always be at right angles to the magnetic field. So we have a way of figuring out which way it goes, and this is called the right-hand rule. And so there's a couple different right-hand rules, and it just turns out nature is right-handed. This is a thing about nature, is the nature is that if you use your left hand, you'll get it all wrong. And the right hand is, that for our conventions, the right hand is correct. And for any left-handed people out there, I'm sorry, but you'll be interested to know that the weak force is left-handed. So there are fundamental rules of nature that are left-handed. We're not discriminating against you. It just happened to work out this way. So, so how you work this out, right, is if you want to figure out which way the force is going, you take your right hand and you have to do the force is going to be which way your thumb points. You're going to point your fingers in the direction of the current. So in this case, the current is going into the page. The camera up a little bit further so I can do this. So the current is going into the page, or into your screen if you like. And then I'm going to curl my forefingers in the direction of the magnetic field. So I put my hand down into the page. That's the direction of the current. And I curl my fingers in the direction of the B field. Then my thumb, if I stick my thumb straight out, it points in the direction of the force that'll be felt. So we're going to do thing one is the current, thing 2 is the field, and thing 3 is the force. And so if you can remember 1, 2, 3, first your fingers, then the curl, then your thumb. 1, 2, 3. Some people teach it like this, where you hold up, so it's first finger, second finger, thumb. That's another way you can do it. So if you put your forefinger pointing in the direction of the current, your second finger pointing in the direction of the B field, and your thumb then points in the direction of the force. And there's like 10 variants of this. And you may have been taught a different one. If you're comfortable with a different right-hand rule, use the one you're comfortable with. I prefer this one though. I prefer the curly hand one because it instills an order of operations. First, put your fingers along the I, then curl them towards the B, and the thumb tells you which way to go. Right? So the same thing here, and you can do this yourself. If you have the current is coming out of the page, and then you curl your fingers in the direction of the current, so then the force will be up. So that tells us how to find the direction. Now, if you want to work on, so it's worth talking about the math of this. So what we find when we do this is, let's just focus. So what we find when we do this is, so we have this wire carrying this current, and we have, say, a magnetic field. And so this thing will feel a field. Okay, so let's get this right. So the current is going this way, and the field is, let me see, the field is away from us because it's showing X's. So the field is away, so my thumb points up. So this thing will feel a force that way. That's going to be the direction. So what we find is the magnitude of the force is proportional to how strong your magnet is. The stronger your magnet, the more the wire will wiggle. And this is something you guys can find out when you're playing with your magnets and your wires. Another thing you'll find out is that the force depends on how much current is running through the wire. If you double the current, you double the amount of force that's acting on the wire. It doesn't have anything to do with the mass of the wire or how many electrons are on the wire. It has to do with how rapidly that current is moving. And it also clearly depends on how much wire you have in this magnetic field, right? If I put in a second section of wire, then I also feel a force on that section of wire. And so the force clearly has to depend on how much wire I have that's running through that magnetic field. So if I have more magnetic field and more wire, then I'll have a longer wire and it'll feel more force. So every section of the wire feels a force. Now, how we write this down then is the size of the force. And it turns out there really aren't any other things that this matters on. Is the size of the force is equal to I times L times B. That turns out that those are the units that actually work. Where B is our symbol for magnetic field, and we haven't actually introduced this, it's got units of newtons per amp meter, which is, let me see, it's a kilogram per second squared amp. And we have a name for this. We call this a Tesla. Named after Nikola Tesla, who did all of this amazing work with electricity and magnetism, and what's the car is named after. So we measure this in Teslas. 1 Tesla is a very big field. It's an extremely large field. 1 Tesla is approximately the field that you will get if you are put into an NMR, into an MRI, right? A magnetic resonance imager, the big tube that they slide you in and then take pictures of your insides. An MRI tends to have a magnetic field of about 1 Tesla. This is a really big field. The Earth's magnetic field, I think, is like a 0.5 millitesla, something like that. So so a Tesla is a very, very big field. Normally we'll work with millitesla instead of that. So if you declare that this is the units of a magnetic field, then we have a magnetic field, and now this gives us a way of measuring magnetic field. So this tells us how it works. Now, this is how much force you get, though, if everything is at right angles. So one thing you can have is if you don't have things at right angles. So for instance, if I have my magnetic field like this, and my current is like this, right? So if my current was coming out of the page and my magnetic field is going into the page, well, if you try to do that, I put my fingers along the current and then I try to curl it, I don't know which way to put my thumb. So it turns out that there's no force here. So it depends on what the angle is between the current and the field, right? And so really it's going to be, the force is going to be equal to I times L times B times sine theta, where sine theta is the angle between B and the wire, which I'll just say is the L vector. So I'll just say if I have a wire, it has length L, and that's going to be the vector L. Now, okay, we've got a sine theta, and we've got this thing is a vector, and this thing is a vector. Hold on. We've seen this before. What we can write is F is equal to I times L cross B. And this is something we saw earlier in the first physics course, where the cross product is explicitly an operation that tells you how perpendicular two vectors are. So this is so firstly, the size, the magnitude of this is maximum if the two vectors are perpendicular, and it's 0 if the two vectors are parallel. And it's something in between if there's something in between. You guys remember where we saw this turn up in 1500?
Torque.
Torque, that's exactly right. We had torque is equal to R cross F. But it also has a direction. So L cross B creates a vector, and you find what it is by the right-hand rule. If you put your hand along I and curl it towards B, that gives you F. And so it turns out that anything, A cross B equals C, always has C in the direction of the right-hand rule, where you point your fingers along A, you curl them towards B, and C is the direction of the answer. So this right-hand rule this encapsulates the right-hand rule. When I write this, if I write that cross product, that means I'm using the right-hand rule. So let's see if we can get a couple of these. Oops. And one thing I will tell you is never try to do it without your hand. I get my hand out for this every time. I have to pick up my hand and physically put it in front of me. Maybe I might do it under the table or something where nobody can see me, but I will always get my hand out and actually do it. My what is it called when you know where your hands are? Your perceptive sense. Okay. So the current is running to the right, and I curl my fingers in the direction of the B field, and so my thumb points out of the page. So you're right, that's E. Correct. Very good. Yeah, it's E again. You're right. Fingers curl up. Now, what's going to be different in this case if I do this? From the last case where I had the current traveling this way. What's going to be different?
The magnitude of the
Basic
force.
component forces.
That's right. The magnitude, right? It's not going to, so the wire in both cases is going to get pushed up, but here the wire won't get pushed up nearly as much. And if I put the wire like this, it won't get pushed up at all. So if the wire is running straight up and down, there won't be any force at all. Very good. All right, one more. Stephen's all believing me. Okay, got a couple of nones of the aboves and a couple of B's. Okay, so unmute your mics and convince each other.
So the reason I said none of the above is because he was saying earlier that there'd be zero force if there was not, if it wasn't in a direction that you can use the right hand rule on, basically, is what I understood.
Yeah, now I see that because the force and the B would be pointing in the same direction.
Well, let's see. So let's see if we can do it. So you're right, Stephen. If we can't do it, if we can't figure out which way to turn our hand, then that means there can't be a force. But let's see if we can do it. So if I put my fingers along the direction of the current, right? And now the B field is pointing out of the page. It's pointing at us, right? It's pointing out of the screen. So if I put my fingers along here and then curl them, I can have I can say that these two things are at this angle, which means that the force has to be pointing down and to the right. So it's going to be.
That makes more sense.
Right? You with me? Okay, good. All right. We're going to have more of these if you need so many practice. All right. So let's say I have it put it together. Let's say I make a square loop of wire and I put a little battery in it to make the current run around the loop. What's that thing going to do? Now this is using, I should write IL. All right. Somebody have a go at answering this. Oh, I should say, if you feel awkward talking, pop open the chat. This is something we could try is, see, how do I open my chat window? I'm not sure.
I just thought since all the forces are in opposite directions, they would just probably go out to zero.
Right.
Yeah, that's what I'd say too, because they're all the same length.
So it's worth drawing this diagram here. So here's the top one, let's say. So which way the force is which way is the force going to be on the top wire? It's going to be towards the top of the page, right? It's going to feel the force that way, right? And then so then I have the bottom section, and which way is its force going to be? Down, right? It's going to be down towards the bottom of the paper. So I'm also going to have these two sections here and here. So this guy is going to feel force, let's see, I cross B, so that's going to be that way, and that one's going to be that way. So all these bits of wire are all going to pull outwards. And so, in fact, what's that going to do? It's actually going to pull on the wire and might deform it into a circle or something like that. But there's no net force. The size of each of these is the same because it's the same length and the same B field and the same current. So the size of each one of these 4 black arrows is the same. And so nothing happens to this loop. This loop feels no force at all. This is a very boring example. We'll get to less boring examples later on. So that gives you the idea of what's going on. So now, why currents? So now let's get into it. So we know that what's happening inside this wire is a current is really just little bits of charge moving around. So if we have a current this way, let's imagine I had a tube full of, say, sodium ions or something. So what I'd have is I'd have little positive charges moving this way, right? That's what a current is this charge is moving, right? A current is dq dt. So, knock all my stuff off. So what must be happening, right, is that inside this wire, what must be happening is the magnetic field must be pushing. So here's just the same example as last time. So I have a magnetic field like this. What must be happening is that each one of these little guys is feeling a force. Let me see, do I have this right? So I cross, yeah, okay. So each one of these little ions must be feeling a force, and that force is acting on the ion, and it's bumping into the pipe or something and pushing the pipe up. That must be what's going on, because that's the only difference between a tube without current and a tube with current, is it must be true that the individual charges are feeling that force. So that must be what's happening on the microscale. So these little charges must be being pushed. And we know that this is talking about how much charge is being pushed. Okay. Well, we have this force is equal to I L cross B. Well, that means that this is going to be dq dt L cross B. Now let's see if we can get any further with that. So let's say I've got a section of tube and its length L, right? And let's say, and we're going to have a current, and here I'll just use deltas, dq, delta q, delta t, right? Now, the amount of charge that goes through this tube, that amount of charge is going to be equal to, let's say I have it so that all of these charges, I make L the right length so that dq charges flush out in time delta t, right? So let's say I have all of them go distance L and dt. So I have delta Q is going to be the number of little ions I've got times the charge of each little ion. And delta T is going to be equal to, the speed, V, is going to be L over delta T, right? So this is the speed at which each little ion is moving. So that means the current is going to be delta Q and little q over L delta T. Or sorry, that's wrong. N delta Q over delta T. So let's get this. So then delta T is equal to L over V. So this is going to be NQ over L times V. So now I have a new expression for the current. So now if I put this in, and I'll just use the absolute values here just to make things easier, I have the current, so it's ILB, and the current is NQV over L times B. Okay, if I do that, okay, those L's cancel, and I'm left with NQV times B. So I'm left the N and the Q. So this is how many little guys I've got in my tube. I've got N little guys in my tube. Each one has got charged little q. Each one is moving at velocity v, and B is the size of my magnetic field. And this tells me the total force on the whole thing, right? But also, if I put the vectors back in, I can even put the vectors back in, that the direction of L, the L vector, is going to point in the same direction as the V vector, right? The L vector is which way my wire is pointing, which way the current is going, but that's got to be the same thing as the net velocity on all my little charges in there. So in fact, I can write that the force is going to be equal to N times Q times the direction of V, which is the same as the direction of L, cross the direction of B. And so this is the net force on the wire. So now if every little charge Q is contributing to it, the force, so this is the force on the wire, the force on each little charge has got to be Q V cross B. And this turns out to be the fundamental rule that's driving how wires feel magnetic fields. The wires feel fields because the individual charges feel fields. So an individual little charge Q feels a force, but it only feels a force if it's moving, right? A charge that's just sitting there doesn't feel any force. But if it's moving through the magnetic field, then it starts feeling a force. And this turns out to be the thing that's really going on underneath the hood. Currents, of course, are the things we can do on a macroscopic scale most of the time, but we can actually do this. So this is the actual microscale thing of what's going on, and the same rules hold as they did before. So oops, that's stupid. I don't know what happened there. Forgot that one. That one's a bad copy. Sorry about that. Don't know what happened there. And again, if you're not sure, you should always have your hand out. Okay. Caleb, I can see your ceiling, but I can't see you. That's okay. You have a very pretty ceiling. Right. So yeah, so B is the right answer, right? If I push so it's always first thing cross second thing equals third thing. So the first thing is my fingers, and that's the V, that's the direction the particle's going. B is away from me, so I curl my fingers down, and my thumb tells me which way it's going to get pushed, which is the B direction. So that's correct. The B is the So that's the right answer right there. Okay. Let's do another one. So remembering how vectors work, let's say it's a negative particle, like an electron. Yeah. Why? How do we know this?
Because it's going to move in the opposite direction of the field.
No, it's still moving this way, right? The particle is still moving this way. The V is still in that direction. So if we're using this equation here, what have we changed?
Q.
Q, right? So I've multiplied this vector by a negative number, and when you multiply a vector by a negative number, it swaps direction. So that's the math we can use. V is this way, V is this way, V is still away from us, so that points to the left. But then if I multiply that vector, the left vector, by a negative number, I get a vector to the right. So A is still the right answer. Now another way, I think what you're trying to say is that if I have negative particles going that way, that means there's a current traveling that way, right? Because you remember how that if the electron is going to the right, the current is going to the left. So if the electron is moving up, the current is moving down. So now, if I use this rule, the current's moving down, and then the field is moving. Oh God, I can't get my hand around. Oh, the field's going that way, and so I push my thumb off to the right, right? So this is a consistent rule, right? Negative particles traveling up are the same as positive particles traveling down in terms of current. So this guy fields a force to the right, whereas a positively charged particle will feel a force to the left. I know it's not quite as good before because everybody can see how everyone else is answering, so nobody wants to like stand out. All right, so let's try it. So V is this way, B is that way. So my thumb can stick out of the page. It's a positively charged particle, so that's all I need to do. So the force must be in direction E. You with me? You with us, Yogesh? Okay. What if I Chris, what do you think now the above?
Well,
Yeah, I got it.
if you use the right hand rule, you can't really curl your hand over since they're both going in opposite directions.
That's right.
So I thought that there was no force.
That's right. That's exactly right. If the particle's coming straight at us and we curl our fingers around, there's no particular reason to point your thumb in any particular direction, right? There's no way to know which way to push, which way it pushes. So this is a case where it's zero. In other words, the angle between V and B is 180 degrees, and sine of 180 degrees is zero. So these guys are parallel to each other. They're anti-parallel to each other, and so here you get no force. Very good. Excellent. Okay, let's do one more example. Now, what I want to do here is I'm going to ask what's going to happen to a particle as it's traveling through this. So let's say I've got a positive particle and the field is like this. It's into the page. So V cross B is a force to the left, so that's the F arrow. So if I wait just a little while, where is this particle going to be and what direction is it going to be moving and what's the direction of the force going to be on it a moment later? So right now, it's here. It's got that velocity, got that force. So a moment later, it's traveling this way. Where is it going to be a moment later? We put a dot where it's going to be, and what its velocity is going to be, and what its force is going to be. So you have a piece of paper out. So I put a dot here. So a moment later, it's moving upwards, so it's going to be something like here, right? Now, it's had a force act on its velocity. So which direction is the velocity now? Yeah, the velocity is going to be that way, and the force is going to be on it. I use a different color. The force will be on it that way, right? So as this thing travels around, it'll have a velocity like that, then like that, then like that, then like that. With the force on it this way, and this way, and this way, and this way. Now, is it going to speed up or slow down?
Slow down.
Why is it going to slow down?
The force is in the same direction as it, so it's slowing it down.
So if I look at it, at any given instant, the velocity and the force are always at right angles, right? So they're always like this. And so let's say there's no other forces that are acting on this guy, right? So if my force is at right angles to my velocity, is my velocity getting bigger this way or getting bigger that way? It's neither, right? Because this guy, right? Or I've got these guys backwards. So this guy is neither making this arrow bigger this way, nor is he making it bigger this way. What he's doing is he's changing the direction of the velocity, right? We've seen this before. This is just uniform circular motion, right? We've seen this before. The velocity is perpendicular to the force, and as long as you have that, you have a thing moving in a circle. And this is the same as like a ball on a string, where the tension force is always acting towards the center of the circle. Or this is like a planet going around a star, that the force is always towards the center of the circle, and so you have this. So what this thing is going to do is this guy is going to move in a circle like this. The circle is going to be tangential to the magnetic field, and he's going to be moving around like that. This is actually a very, very cool effect, and is the basis of a lot of different technologies that we've got going on here. At every given time, right, as long as he's not speeding up and slowing down, his speed isn't changing. And if he's in a constant magnetic field, then B isn't changing. And of course, his charge isn't changing, which means the force is staying the same all the time. So at any given place, he's got the same force. He's got this force, which is Q D times B. And if we always have it that his velocity, if his velocity starts out perpendicular to the field, it stays perpendicular to the field because the force is always also perpendicular to both the velocity and the field. So the field is like out of the page, it'll stay always at 90 degrees. Like this is at 90 degrees to the field, this is at 90 degrees to the field. Anything that's in the plane of the paper is at 90 degrees to the field. So we know what the rule is. If I have uniform circular motion, I have a centripetal acceleration, which is equal to v squared over r, where r is the radius of the circle. So we know that F equals ma. So F equals ma, which in this case will be a centripetal acceleration, so that's mv squared over r. And we know that that's going to be equal to the force we're applying, which is Q times V times B. So if I move this around a little bit, I can say mv over br. Do I have this right? Yeah, mv over, q times b is going to be equal to r. Do I have that right? Yeah. This is called, so this radius, if I have this, this is called the cyclotron radius. Which is pretty cool. And in fact, if you look at the top of this, that's momentum. M times V is momentum, so it's actually P over BQ. So this thing tells us how big a circle we will have. If the particle is moving very fast, it'll be a very big circle because it's moving fast. And there's a competing effect here that there's a very strong magnetic force, but you need a very strong force to make it turn into a circle. And so it turns out that this part wins, and so the circle gets bigger as it goes faster. If you increase the magnetic field, then the radius gets smaller, and so your circle tightens up if you increase the magnetic field. If you turn off the magnetic field, then the radius goes to infinity and the thing just goes in a straight line, right? This has got an infinite, if it's going in a straight line, right? And it's going in a tight little circle, then r is small. And it's got a big charge, clearly that also affects it. So this is the thing that we can use to do things. And in fact, one of the things we can do is we can track particles moving. So this is, for instance, how we know about the existence of certain subatomic particles, is we have a tank of stuff. In this case, it's a superheated steam or something like that. I forgot exactly what it is. And you have particles, invisible particles, and I think in this case they're coming from this direction, and they go through this stuff. These particles may sometimes interact with a particle in the steam, a molecule in the steam, and so what it does at that point is it creates a charged particle. A charged particle moves to the steam, and as it moves to the superheated steam, the steam condenses and creates a small cloud trail, and you can take a picture of that. This was done in the 50s. 50s or 60s is this picture. And you can see this trail of this particle. It's called an ionizing particle. And so it creates this little cloud trail here, and there's another particle creating a cloud trail here. And then you put a magnetic field through this thing. Now let me see, I'm gonna guess that the magnetic field, let me see if that's the force, that's V cross B. So I'm gonna guess the field was away from us in this picture. And so what that does is it makes some of those particles curl into circles. And then as it slows down, the circle changes radius. So you can tell whether you have a positively charged particle because you can look at the direction it curves. So this particle started in here and it's leaving. It's going outwards. Okay, why are you guys saying A? Or B, or whatever.
So the way I understood it is that the velocity that's going outwards, that was how I faced my hand, and then the magnetic field is out towards the page.
Right, so it's towards you, yeah.
And so it's roughly going along what it would appear to be versus just being flipped.
right? So it's going this way, and the B field is towards me. So if there's a positively charged particle, it should feel the force to the right. So is this guy feeling a force to the right or the left? Is he going this way? Is he feeling a force to the right or feeling a force to the left?
Right.
No, because he's curving to the left, right? He's getting pushed into a circle moving leftwards, right? So the force is that way on him, right? He's getting deflected to the left. So if he's getting deflected to the left, his velocity is this way, and the B field is out of the page. And so it's a force to the left, this Q must be negative, because if he's positive, V cross B would be to the right. So if he was a positively charged particle, he'd bend away this way. But he's a negatively charged particle, he'll bend away that way. This is going to be a negative one. Okay, I can tell people are getting pretty tired today. This is these rules. There's going to be a lot more of them. This isn't the end of our discussion about right-hand rules and this sort of thing. But we are going to have plenty of time to do more practice with this stuff. Next time, I'm going to come back to the idea of particle accelerators, and I'm going to show you, ask you a couple more questions about how they work. And one of the things this naturally leads to is a couple of things that are very useful in other things. So for instance, a mass spectrometer basically works on this principle. So we use this in particle detectors. We use this principle all over the place. So this is actually a really, really important piece of equipment. And it also moved into a device called the cyclotron, which was one of the very first particle accelerators. And so this is the kind of thing that we use all the time. This gets used in televisions. This gets used in TV cameras, or at least old style ones. This gets used all over the place. So so this isn't just abstract stuff. This is actually the sort of thing you're going to be using to build real world objects, including motors and generators and all that sort of thing. So we're building into the rules that are fundamental. It's really hard to teach the right-hand rules this way, so I hope that people are getting it. What you really need to do is like look at your textbook and make certain that you can guess the right answer for those, because people are hitting about 75%. So, and I don't, probably because people are getting tired. So we'll continue with this on Monday. Please try to get me some version of your homework by then. If you haven't already dropped it off at school, I'll run into school to pick up any hard copies tomorrow probably. Also, if you haven't, pick up your lab kits at school. And if you can't pick up the lab kits, let me know and we'll arrange something else. Okay? So have a good one. Have a good weekend.
When's our next homework due?
Sorry again?
When's our next homework due?
I don't know. I'm sort of planning for maybe a week from Monday, but we'll see how it goes. I don't know how fast we're going to go under this new regime, so I don't want to make it too soon. And I'm going to be pretty relaxed with the homework deadlines, just because this is crazy. But it does mean I'll have to put up the solutions late, so there's a trade-off there. So we'll try to do the best we can. Okay. See how it goes when we do it. And you have a beautiful ceiling fan. I love your ceiling fan.
Thank you.
Okay. All right. See you guys on Monday. Great job, everybody.